Okay, um, so today we're going to wrap up chapter 4, and so let me just talk a little bit about our, how this works here, okay? So chapter 4 is all about relationships between two numeric variables. And we said we can fit a trend line to the data, okay? And so in this case, we are using the variable pages to predict the width of a book, right? So, here's our little picture. We've got a book, and this is terrible drawing, but whatever, okay. So we've got a book, and we're measuring how wide the book is, right? Okay, so, in our diagram, we'll often label these, okay? We have the x variable, and we have the y variable. All right, and the x variable is often called the predictor, and the y variable is often called the response. Okay. The x variable can also be called the independent variable. Okay. And the y variable can be called the dependent variable. Okay, and we have the, it's also called the explanatory variable. Okay, all right, I'm sorry, I guess response actually goes with explanatory variable. And I guess if we're using the word predictor, it should actually be predicted variable. Sorry, my bad. So these are just different names, different ways we can say this is the explanatory variable and this is the predictor variable. Okay, and so we can identify components of our regression equation, okay? So we can identify components of our regression equation. This is the equation of a line, right? So a line will have a slope and an intercept, okay? So we defined how we can calculate the slope earlier. Do you guys remember? Maybe, maybe not. Okay, so the slope we said is equal to r times s of y over s of x, okay? But in our case, what is the value of our slope? 0.0366, okay? Now, how is the width being measured? The width is being measured in millimeters, okay? So what does this slope mean? Okay, so our slope is 0.0366, okay? What this is how much we expect our predicted variable to change if our predictor variable increases by 1, okay? So the slope how much we expect our predicted variable or the y variable, the response or the dependent variable, to change if the predictor variable, the x variable, increases by 1. Okay? So what does it mean to increase our x variable by 1? In our example here. Yeah, if we increase the x variable by 1, that means we are increasing the number of pages in our book by 1. Okay? So increasing, in our case, increasing x by 1 means adding 1 page to the book. Okay. Or not necessarily adding a page to this particular book, but just, if we're looking at different books, if we have one book that's 400 pages and another book that's 401 pages, essentially x has changed by 1. Okay? So then what happens? That means the width of the book, our prediction for the width, changes or goes up by 0.0366. Okay? Our prediction. So it's not necessarily saying that you add a page to a book, the book is going to increase this much. Okay? We're not saying that. We're just saying that our prediction, if we don't know anything else about the book, our prediction is just going to increase. Our prediction for the width increases by 0.0366, what's our unit? Millimeters, okay? And that kind of makes sense, right? Every sheet of paper is quite thin, okay? And essentially, every sheet has 2 pages to it. So the amount that it's going to change by adding 1 page, which may not physically be possible because you have to probably add 2 pages at a time. But anyway, just conceptually, if we could think about adding what it means to add 1 page, that's not going to increase the thickness of the book by much. So it's increasing the thickness of the book by just a very small amount. It's not zero. I mean, it's not 0, but it's a very small amount, okay? All right. On the other hand, you might have another variable where an increase of 1 is a huge change, okay? So let's say we were I don't know, measuring people's scores as a percentage or something like that, okay? Or a ratio. So let me think here, okay? So here, let me just write this out, okay? So sometimes adding 1 to x is very insignificant. So the slope will have a small value. Okay. Sometimes adding 1 to x is a very huge change. Okay. So, okay, here's an example. All right. Are you guys familiar with baseball at all? Maybe, maybe not. Some of you, yes. Okay. So in baseball, we have all sorts of statistics for baseball. One of the classic statistics is batting average. Okay. And if you followed up with modern baseball, batting average probably doesn't get as much respect these days anymore. We've kind of shifted over to other sabermetrics like on-base percentage and whatnot. Okay, but the concept of batting average is, did the player hit the ball, okay? So a hit is the player had to hit the ball and make it to first base, okay? Just contact between the baseball and the bat is not enough because that happens quite a bit, but a lot of times it ends up in an out or something else, okay? So it has to, so a hit is contact with the ball and the player was successfully able to at least reach first base, okay? Hit the ball. I'll say contact with ball. First base, at least, okay? So, you know, home run. You know, I guess, I assume everybody is like kind of familiar with baseball, but maybe some of us are not, okay? So in baseball, you know, there's a player here. This is guy, the pitcher, he throws a ball. There's another player down here, he's got a bat, and he throws the ball. This guy tries to hit the ball with the bat, and then when he hits the ball, he runs, okay? And it's quite hard, okay? It's quite hard to, because these balls are coming at you like 90 miles per hour, okay? It's, and they're, you know, good pitchers will put like a curve on it, so, you know, you think the ball's going over here and it switches direction. And then, well, anyway, these are like pros, okay? And they still have a hard time hitting the ball because the pitchers are pros too, right? You know, you got these people who are batting. So anyway, they make contact and then they run, okay? And everybody is excellent at what they do. And so, you know, they're really good at getting the ball and getting it to first base to get you out. So it's quite hard, okay? And so the batting average is how many hits you got divided by, they're called at-bats, which is almost like how many opportunities you had to hit the ball, okay? Like, it's loosely a number of opportunities to hit the ball. Kind of, okay? Because we subtract off, you know, whatever, okay? So it's a little bit different from a plate appearance, but pretty much, okay? And so, you know, what's the average batting average right now? So you know, this is like if you hit the ball every single time you went up to bat, your batting average would be 1, okay? So, you know, the max would be 1, which nobody has ever had a batting average of 1. You'd say, I'm batting 1,000, which, okay? And then the minimum would be 0. This, like, the pitcher who never makes contact with the ball. Huh? Yeah, so, you know, usually kind of the average is maybe in the mid to upper 200s, okay? You know, and I'm sorry. So when I say 200, I mean like 0.27 or something like that. Okay. So this is probably like a decent batting average. I don't know what is the current average batting average. What is that? MLB statistics. Okay. So the batting average leaders are around 0.333. Okay. These are the best is at around 300, and then yeah, and then so you know the top 40 is around 0.26. Okay, so this is pretty good. Pretty good. You know, if you're over 0.300, this is excellent. Okay, and then you know probably like 0.22. This is mediocre. Something like that, okay? So these are kind of like batting averages. So a lot of time, you know, if you never watch baseball, but then you go into a bar and they're playing baseball on TV, a lot of times when the player goes up, they'll show their batting average and they'll say like, this is how well they've performed this evening and whatnot, okay? So anyway, you know, the difference between a mediocre player and an excellent player is like 0.08, right? So if we were trying to make predictions and we were using batting average as our x. So if x were our batting average, okay, then the slope would have a ridiculously high value, right? Because the slope says we're adding 1 to x, okay? So adding 1 to x is a ridiculous change, right? We're you know, the difference between a bad or a mediocre player and an excellent player, you've got, you know, 8/100ths of a point. So adding a full number 1 is like a unheard of change. It's an impossible change in batting average, okay? Adding 1 to x would be a large, you know, impossible change. Okay, it is, you know, not possible to add 1 to 0.22. Okay, so the slope associated with this would be incredibly huge. It would probably, you know, if you wanted to predict the number of runs based on someone's batting average or a team's batting average, adding 1 to your x would change, you know, change the number of runs by a very large quantity here. Okay, does that kind of make sense? So in this case, you don't want to make a direct interpretation based on x, okay, or based on the slope. Okay, you'd probably want to divide that by 100 and say adding 0.01 to the batting average, you know. So let's say the slope, whatever it is like 16,000. Okay, you would say, okay, this is huge, right? So the interpretation of the slope, you'd probably want to base it on, if we increased x by 0.01, you know, if we increase x by 0.01, then we predict y changes by what? Not 16,000, but 160, right? Because we're just changing x by a small fraction. Okay, and this will probably be a more meaningful interpretation. Okay, and so this week you'll have a new lab tomorrow, and actually I think deals with baseball, so it's good. If you're completely unfamiliar with baseball, it's okay. You'll still be able to do the lab. Okay, it just might not be as interesting. All right. Have you guys seen the movie Moneyball? Yeah? Okay. So if you haven't seen the movie Moneyball, it's not required to watch it, but it's a good movie, okay? And it talks about, you know, kind of the shift away from these traditional methods of evaluating players to ones that are based more on data, okay? And they skip a lot of the math, okay? But you guys get to do the math tomorrow in lab, so I think it's cool. I love this stuff, but then again, I'm unbiased towards all of this. I told you this is my dream job. I guess I have another dream job, and that would be doing sports analytics for a team. But I love teaching too, so I would love to teach classes on sports analytics if there's a demand for it. Okay, let's try a couple clicker questions here. That's our favorite part of the day. Okay. All right. Oh, I gotta turn on the clicker base. Hang on a second. Is this clicker thing, are we feeling okay about it? No? Huh? I shouldn't ask questions like that. Of course I'm gonna just get a sad answer. Okay, hang on. I apologize that the remotes themselves are expensive. but it does offer a certain amount of interactivity, which was not possible before in this lecture setting. Okay, so try to answer this question. I hope you guys can see it. It says the following is a prediction equation for the relationship between the value of the vehicle and its age in years. Predicted value is equal to 21,375 minus 1215 age. How much do we predict a five-year-old car? 5-year-old vehicle. Okay. So sounds terrible. And actually, that's, you know, well, I guess the sad part is that the sale of humans does actually exist. And anyway, okay. So we're clicking away and we're getting answers here. Okay, I think that's about correct. All right. Okay, so yeah, you just plug in the number 5 into here. And what happened? Why can't I? Oh, here we go. Okay. And yes, the answer is indeed C. Okay. There you go. Now, yeah, the vehicle of age in years. Now, if I said, and its age in months, how would that affect our slope? If we measured age in months, so this is a different. Oh, here, I'll make another clicker question right here. All right, yeah, let's do it. Let's do it. Okay. Question 2. All right. Okay. So if age was recorded in months rather than years, our slope would be okay, unchanged. B, 12 times bigger. C, 1/12 as big. Is that? I think that's how you would word it. Okay. All right. Let me start a new question here. Does this question? Oh shoot. How do I hide this? Okay. All right. We'll just try it. Okay. So if age was recorded in months rather than years, our slope would be yes.
Is the equation the same? Are you just changing the age and the...
Oh, okay. So here, I'll okay, I'm going to flip back. And so this was the old equation. This was the equation when age is recorded in years. And my question is, so this is equation for when age is in years, okay? And so if we recorded the age in months rather than years, how would that affect our answer is basically the question here. Okay, so we'll say 10 more seconds, just click something. We'll see what happens here.
So you're not changing the 1200 part, right?
Huh? This is, okay, this is the equation when the age is recorded in years. The question is, if I recorded the age in months, would that change our equation? Well, that doesn't matter, okay? Because we're not trying to predict the an actual car. We're just saying what happens to the equation. Okay, I'm gonna call time here. The numbers haven't really changed. Let's see what you guys said. Everyone's so scared. Don't be scared. Okay. How do I click, click, click? Ooh, okay. This is like this is the election, right? Okay. How's it gonna be? Okay, the answer is dun 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 dun. C. Okay, all right. Everyone's angry now. Not everyone. 42 plus 60% of you might be upset. Okay. All right, so what's going on? If you answered unchanged, if the correlation remains unchanged, okay? The correlation between age and value would be unchanged. That is not affected by units. Correlation is not affected by units. However, okay, if we think about this, right? A 5-year-old car would be how many months old? 60 months old, okay? Now, if I plug in 60 here, what's my predicted value going to be? It's going to be like negative, $40,000 or something, right? 12, 15 times 60 months, okay? It'd be like negative $50,000. Now, does that make sense? That does not make sense, right? So what happens is that our predicted value, the slope here, becomes 1/12 as big. Our slope becomes about $100 per month, okay? Yes, and so when you change the units, the slope changes, but the correlation does not. We have a question.
From a mathematical standpoint, couldn't you just multiply, like doing an inversion, whatever age is there, by 12, and then have it built in the formula, so then just plug in the age and months?
Okay, so yes, you're essentially doing the conversion prior to plugging it into the equation, which is not what we have, okay? Essentially you are saying so what you are saying is do age in months divided by 12, right? You're going to say take your age in months, divide that by 12, and then plug that in. That's what you're saying? If the age is recorded in months, right?
Just like if you just do like a regular unit conversion, it'd be like 12 months over 1 year, because that's 1 year's approximate.
It would be 12 months in 1 year, okay? So the conversion from months to year would be a division of the number of months. 60 months divided by 12 is 5 years, right?
My conversion is from years in the equation to months.
Yeah, but the age is being recorded in months, okay? So if you take your data, we're taking our data, which is recorded in months, right? How many months old are you? You're like 240 months old, right? Okay? That's it if today's your birthday month, okay? So if you're like 240 months old, then your age is 20 years, right? So we're taking, if the age is recorded in months rather than years, okay? In order to use this thing, we would have to take our age in months, divide by 12, okay? Effectively, I'm just taking this division by 12 and putting it right here, okay? So the predicted value of the slope changes. So I think maybe that's worth writing here, okay? So changing units will change the slope. Okay? Changing units does not change the correlation. Okay, and so if your equation is going to take your measurements as they are recorded, you know, your slope might change. Okay, all right, last clicker question in our session here, right, or for this part. So this is clicker question 3. So here we've got the predicted value, again, age measured in years. Okay. Choose the interpretation of the slope. It says new car would be worth $21,375. The value of the car is the product, not the produce, product of the age of the car in 1215. Each additional year will reduce the car's value by 1215. Our predicted value decreases by 1215 for each additional year in the car's age. Okay. The answers aren't all the same, all right? There are differences between even the answers that sound the same. They're not the same. Okay, we'll say 10 more seconds. So just pick your answer here. So this is asking for the interpretation of the slope. Okay, we'll hit the stop here. Okay, let's see our chart. And our answer choice is D. Okay? So what's the difference between these, okay? The key is our regression equation is an equation for our prediction, our predicted value, okay? And so adding 1 to x, increasing the age, okay, for each additional year in the car's age, so that's adding 1 to the age, that changes our predicted value by negative 1215, which is our slope. Our slope is minus 1215, so adding 1 to the age changes that by negative 1215. So our predicted value does decrease by 1215 for each additional year in the car's age, okay? Number C is not the same, okay? Because this says each additional year will reduce. This is like a statement that this is going to happen, okay? Now overall, the trend seems to indicate that adding a year to a car's age decreases its value, but that is not necessarily defined as 1215, okay? In 1 year, a car can decrease a lot more than 1215. It can decrease a lot less than 1215. Okay, all sorts of stuff can happen, okay? Our prediction, if we don't have any other information about the car, our prediction changes by 1215, but the value of the vehicles themselves don't necessarily change by 1215, okay? And then this is, again, the value is not equal to this. This is the predicted value is the difference between 21,375 and this, okay? Answer A is the interpretation of the intercept, okay? This is correct. It is correct to say that if a new car with age 0, we would predict is worth 21,375, okay? So the intercept of 21,375 basically says we predict that a new car is worth 21,375, okay? All right. Okay, so we have that. talk about the interpretation of the intercept. Intercept, okay? So the intercept in our book's example is 0.622 plus 0.0366, okay? So the intercept, predicted width for the books is equal to 6.22 plus 0.0366 or something like that, okay? The intercept is our prediction of y when x is equal to 0. Okay? Sometimes it makes sense to have x equal to 0. Sometimes it does not. Okay, and so in the example with the value of the car, predicted value of car is equal to 21,375 minus, 1250 times age. Okay, it makes sense, x equal to 0 means age equals 0, or that means it's a new car. And in that case, our predicted value for the vehicle is 21,375. So the interpretation of the slope is the prediction, our predicted value of a new car. Okay, so the intercept interpretation is we predict a new car to be worth $21,375. Okay. Over here, for the books, it would be we predict a book with no pages in it to have a thickness of 6.22 millimeters. Okay. With 0 pages to have a width of 6.22 millimeters, okay? And so as far as books go, we can kind of have an interpretation of what that means in our mind by saying that is maybe the thickness of the covers, okay? So you can think of how thick the covers of the book are. Maybe the cover thickness is 6.22 millimeters, okay? If we were to try to create an equation between someone's height and their weight, we can create a prediction equation showing the relationship between someone's height and weight, okay? We can say, based on someone's height, we predict their weight to be this. In that case, it does not make sense to have x equal to 0, because that means the height that we are using to make a prediction would be a height of 0 inches, okay? It is not possible for someone to have a height of 0 inches, okay? I guess if you looked at, I don't know, yeah. You can't have a person with a height of 0 inches, okay? So you won't have an interpretation, a proper interpretation for the intercept, okay? And sometimes you get a negative intercept when the answer can't be negative, okay? So maybe we were trying to predict someone's GPA based on their test score or something, okay? Maybe the intercept is negative, okay? Well, nobody can have a negative GPA, I don't think. That would be kind of sad, right? And in that case, the intercept does not have a meaningful interpretation, okay? But the intercept Okay, otherwise would be our prediction for y when x is equal to 0. Okay. All right, we have a few warnings about the regression equations, okay? Okay. All right, so warning number 1, okay? Do not make regression lines if the data is nonlinear, okay? Or the data relationship is nonlinear. Even if you have very high correlation, I gotta set a guard outside that door. If the data relationship is nonlinear, even if there's high correlation, okay? So you can have a situation like this, okay? And in this case, you know, your R is probably gonna be something like 0.9, okay? But a straight line is no good, okay? Do not fit a straight line. So always, you know, this basically means always graph the data first to make sure the relationship is linear. Okay. Point number 2. This is kind of our mantra of the chapter. Correlation is not causation. Okay, just because two things happen together, even if you can make a nice, handy relationship between x and y, we cannot say that one causes the other. Only from a controlled experiment. And this was a question that I think some of you guys missed on the quiz, was that from the controlled experiment, you can make a cause and effect relationship, okay? But if we're just creating relationships between x and y and it's not coming from a controlled experiment, correlation is not causation, okay? Another point, okay? Outliers can really mess things up, okay? So I think I gave the example of shoe size and IQ, right? No? Maybe? Okay. Shoe size and IQ. So if you have data like this, shoe size and IQ should be uncorrelated, right? Shoe size and IQ. But again, if you have a spot out there, you're going to have you can get a regression equation, and now you're going to think, you know, if someone's shoe size increases by 1, their IQ goes up by 3, okay? That's very silly, okay, to make something like that. So outliers can really mess things up. You got to be careful. Always create a graph and check for outliers, okay? And then do not use the equation, do not use a regression equation to make predictions where you have not collected data. And this is probably the most commonly violated warning, okay? So, for example, and I'll make this quick, don't worry. Let's say, let's say you have a child that you are observing, okay? And as soon as the child is able to stand, okay, let's say you start taking measurements. So at age 1, let's say the child can stand at age 1. And so from age 1 to 5, you have measured this child's height, okay? And you see a steady trend of this child's height increasing. You know, every time you measure this child's height from age 1 to 5, you see this child getting taller, okay? So you can then say, oh, well, by the time this kid is 50 years old, he's going to be the tallest man in the world, okay? Because at this rate, he's going to be 30 feet tall, you know? 30 feet tall by age 50. Okay? And we know that's silly, right? Because we know people grow, and then, you know, once you're like 15 to 20 or something in that range, you kind of stop growing, okay? So it seems silly, this is a silly example, but we see this all the time, okay? I cannot tell you, you know, just today I was on the, I don't know, just browsing the internet, and says, you know, study shows that by the year 2050, our oceans are going to look like this, or by the year 2050, this is what's going to happen. Okay? Well, the fact is just because a trend has held up for the last 10 years, we don't know if that's going to hold true for the next 20 years. Okay? Even if it's held true for the last 50 years, we still have no idea what's going to happen in the future. So don't use regression to try to make predictions where you have not collected data yet. Okay? So that's that for warnings there. Okay, we'll see you guys on Wednesday, and you'll have a lab tomorrow in class, or in